Did you know that the sun's activity can disrupt power grids, knock out satellites, and even endanger astronauts? From massive solar flares to powerful geomagnetic storms, space weather has an extraordinary impact on our modern world. But what exactly happens when the cosmos decides to unleash its fury? Join us as we dive into 7 astonishing ways space weather shapes and challenges Earth's technology, revealing a hidden force we rely on but often overlook. Satellite communication disruptions. Satellite communication systems are highly vulnerable to space weather, with solar flares and coronal mass ejections posing significant threats. High-energy particles and electromagnetic radiation from these events can interfere with the radio waves satellites use to communicate with Earth. Disruptions caused by solar storms can affect television broadcasts, internet services, and GPS navigation. These interruptions create cascading effects in industries reliant on real-time data, including aviation and maritime operations. For instance, navigation systems may become inaccurate during solar storms, leading to delays and safety concerns. The physical infrastructure of satellites also faces risks from charged particles during solar storms. These particles can accumulate on satellite surfaces, causing short circuits and damage to onboard systems. Operators often place satellites in safe mode during heightened solar activity to protect sensitive components. While this precaution minimizes damage, it halts the satellite's operations temporarily, impacting services like telecommunications and weather forecasting. Prolonged space weather events can accelerate satellite degradation, weakening materials and reducing solar panel efficiency. Such degradation shortens satellites' lifespans, raising economic and operational concerns as the world increasingly depends on satellite networks. Past geomagnetic storms have caused millions of dollars in satellite damage, highlighting the stakes involved. To counter these risks, advanced monitoring systems and better satellite designs are critical. NASA and NOAA track solar activity to provide early warnings, helping operators prepare. Radiation-hardened materials and enhanced shielding are also improving satellites' resilience, ensuring uninterrupted global connectivity despite space weather challenges. Power grid failures. Power grids are among the most vulnerable systems to the effects of space weather. Geomagnetic storms caused by solar activity can generate geomagnetically induced currents in the Earth's crust. These currents infiltrate power grids, overloading transformers and disrupting their functionality, leading to widespread blackouts, as seen during the 1989 geomagnetic storm that caused a 9-hour outage in Quebec, Canada. The infrastructure of power grids experiences significant stress during geomagnetic storms, especially transformers, which are crucial for electricity distribution. Overheating and physical damage from induced currents can cause transformer failures, increasing the risk of cascading outages that can spread across regions. The risks are heightened in polar regions, where geomagnetic effects are stronger due to proximity to Earth's magnetic field lines. Power grid failures have far-reaching consequences beyond immediate outages, impacting essential services like hospitals, communication networks, and transportation systems. Prolonged disruptions can result in financial losses and safety risks for affected populations. The integration of smart grids and renewable energy sources adds complexity, amplifying the challenges of maintaining grid stability during geomagnetic storms. To mitigate these risks, scientists and engineers focus on real-time monitoring of solar activity and geomagnetic conditions, providing utility operators with early warnings. These alerts allow preventive measures such as adjusting grid load or shutting down vulnerable systems to be implemented. Advancements in transformer design and protective technology, like geomagnetic storm detectors, further enhance grid resilience, ensuring reliable electricity despite space weather challenges. Satellite damage and orbital hazards. Satellites, essential for modern communication and navigation, are highly vulnerable to space weather. Energetic particles from solar storms can penetrate a satellite's shielding, causing malfunctions in electronic components and disrupting services like GPS navigation, internet access, and global communications. A significant example occurred in 1994, when a major solar storm caused multiple communication satellites to malfunction, leading to widespread service outages. Radiation from solar activity further challenges satellites by degrading construction materials over time. This exposure weakens solar panels, reducing power efficiency and shortening operational lifespans. Intense solar events can also trigger damaging electric discharges within satellites, potentially rendering them inoperable. These risks highlight the need for rigorous testing and innovation in satellite design to ensure resilience against space weather. Geomagnetic storms exacerbate the orbital debris problem by expanding Earth's atmosphere, increasing drag on low Earth orbit satellites and debris. This alters trajectories, heightening collision risks, and raising the possibility of a cascading event known as the Kessler syndrome, which could make orbital zones unusable. With thousands of satellites already in orbit and many more planned, these risks grow increasingly urgent. To mitigate these threats, engineers use advanced shielding and error correction systems to counteract radiation effects. Real-time monitoring of solar activity allows operators to adjust satellite positioning or place them in safe modes during high-risk periods. Collaborative initiatives like space traffic management systems monitor satellite and debris movements to prevent collisions. By integrating these measures with innovative designs and predictive technologies, we can protect satellites and the critical services they provide to our interconnected world. Impacts on aviation. The aviation industry is significantly affected by space weather, especially during periods of heightened solar activity. Solar flares and coronal mass ejections release intense radiation that can penetrate Earth's atmosphere, posing risks to high-altitude and polar flight routes. Aircraft flying at high latitudes where Earth's magnetic field offers less protection are particularly vulnerable to increased radiation exposure, which can slightly elevate long-term health risks for passengers and crew. Communication systems on board aircraft are also susceptible to space weather disturbances. High-frequency radio waves, crucial for communication with air traffic control, can be disrupted by solar flares causing ionospheric disturbances. Such disruptions force reliance on alternative channels, leading to delays and operational challenges, especially where backup systems are limited. Additionally, these disturbances can complicate coordination in remote regions, increasing operational risks. Space weather can also compromise navigational accuracy, as aircraft depend heavily on GPS for routing. Ionospheric turbulence during geomagnetic storms degrades GPS signals, resulting in location inaccuracies. To mitigate these risks, aviation authorities collaborate with space weather monitoring agencies to receive real-time alerts and forecasts. Adjusting flight paths during solar storms and advancements in resilient communication technologies ensure passenger safety and operational efficiency. Interruptions in radio communications. Radio communication systems, the backbone of global connectivity in many industries, are particularly vulnerable to disruptions caused by space weather. Solar flares and coronal mass ejections release intense bursts of X-rays and ultraviolet radiation, ionizing the Earth's upper atmosphere and disrupting the ionosphere, which reflects high-frequency radio signals. During severe space weather events, this can lead to radio blackouts, disrupting HF transmissions critical for aviation, maritime operations, and military activities, leaving many regions without reliable communication. The aviation sector, especially on transoceanic and polar routes, relies heavily on HF radio for communication between aircraft and ground control. Solar flares or geomagnetic storms can cause sudden loss of these channels, necessitating rerouting or flight delays, and reducing situational awareness for pilots and controllers. These disruptions are especially critical in polar regions where alternative communication systems may also face interference due to space weather. Maritime operations also face risks, as ships depend on HF signals for weather updates and coordination, leaving vessels without crucial navigation information during blackouts. Mitigation efforts focus on predicting space weather events and enhancing communication system resilience. Space weather forecasting organizations provide early warnings, allowing industries to prepare for potential blackouts. Advancements like adaptive protocols and multi-band radios improve reliability, helping ensure stability in an increasingly interconnected and space weather resilient world. Risks to astronaut safety. Space weather poses a significant threat to astronaut safety, especially during missions beyond Earth's protective magnetosphere. Solar flares and coronal mass ejections release vast amounts of charged particles known as solar energetic particles, which can penetrate spacecraft shielding. These particles increase astronauts' risk of acute radiation sickness and long-term health issues, such as cancer. Even in low Earth orbit, such as aboard the International Space Station, radiation exposure rises during intense space weather events, though Earth's magnetic field provides partial protection. Astronauts face not only health risks, but also operational challenges due to space weather. Intense radiation exposure can impair cognitive function and decision-making, critical during emergencies or complex maneuvers. Radiation can also damage spacecraft electronics, leading to failures in navigation, communication, and life support systems. These malfunctions are particularly dangerous during extravehicular activities or critical mission phases, where even brief shielding failures could have catastrophic consequences. Missions to the Moon or Mars involve prolonged exposure to cosmic rays and solar storms, demanding innovative protective measures. During solar events, astronauts must quickly take shelter in heavily shielded compartments within their spacecraft. For surface missions, such as those planned on the Moon, underground habitats or shielding made from regolith are being considered to mitigate risks. To address these dangers, space agencies are developing advanced radiation forecasting systems and improved shielding materials. Personal dosimeters provide astronauts with real-time feedback on radiation exposure, enabling swift protective actions. By integrating these measures, space agencies aim to ensure that humanity's future explorers can safely undertake long-duration missions beyond Earth's natural protections. Effects on global navigation systems. Global navigation satellite systems, essential for modern technology, support applications ranging from GPS navigation to precision agriculture and disaster response. However, these systems are highly vulnerable to space weather events, particularly solar flares and geomagnetic storms. Charged particles from the Sun interact with Earth's ionosphere, causing rapid density fluctuations known as ionospheric scintillation, which distort satellite signals and reduce the accuracy of position, navigation, and timing services. During intense geomagnetic storms, ionospheric disturbances can cause satellite signals to lose lock or fail entirely, resulting in positioning errors that disrupt critical operations such as aviation landings, financial system synchronization, and precision-guided industrial machinery. These disruptions have ripple effects across multiple sectors, impacting both safety and efficiency. Military operations are especially vulnerable, with GNSS disruptions potentially leading to strategic disadvantages. Ground-based monitoring stations detect signal anomalies and provide corrective measures but cannot fully prevent temporary GNSS outages during severe space weather. Researchers are developing complementary technologies like terrestrial navigation systems and inertial navigation devices, which are less affected by ionospheric disturbances, to reduce GNSS dependency. Improved space weather forecasting offers early warnings, enabling industries to prepare for disruptions and maintain resilience in a space-dependent world. That concludes our journey through the incredible ways space weather affects Earth's technology. From disrupting satellites to posing risks to astronauts, these cosmic phenomena remind us of our planet's vulnerability and resilience. If you enjoyed this exploration, be sure to like, share, and subscribe to InnoVision Tech. Don't forget to hit the bell icon to stay updated with our latest videos. Until next time, stay curious and keep exploring the wonders of science.